Hello guys, welcome back to our channel. The paper we are solving today is IGCSE Physics, May-June 2024, and this is the paper 41. Alright, now let's start with the first question. A long tube contains oil. A small ball is held at rest at the surface of the oil. At time t is equals to 0, the ball is released and begins to fall vertically through the oil. Alright, so the ball is just falling through the oil, that is fine. As the ball begins to fall through, the oil, it accelerates. So first they're asking you to define acceleration. We know that the velocity changes with respect to time, that is acceleration. So acceleration can be defined as rate of change of velocity. Why rate? Because it is with respect to time. So always rate should be added. Alright, now let's start with the second part of this, which is figure out the acceleration or the resultant force. So mass of the ball is given. The resultant force you have to figure out. We know that F is equals to ma is there. Now resultant force will be net force, which in this case should be equal to the mass into acceleration. Have they mentioned the acceleration? Yes. So 0.0075 times 2.8 meters per second square. So the answer will come out in newtons. So if you multiply both of them, it will come out to be 0.021 newtons, which is what you need to mention here, 0.021. Make sure to mention the unit. Now, part C, as the ball falls, its V is recorded and a speed time graph is given. Describe what happens to the acceleration between t is equals to 0 and t is equals to 0.04 seconds. Alright. Now, for these kind of questions, we know that, see, when you drop something, its initial velocity is 0. Fine. But as it starts to accelerate, its velocity starts to speed up. It starts to speed up. As a result, at the same time, air resistance increases. So you must have felt it in real life that when you're traveling in a car at a very high speed, the wind also pushes you at a very high speed compared to normal speed. Just imagine you are traveling in a car at 20 kilometer per hour, then 40 kilometer per hour. You take your hand out a little bit. Where will you feel more air resistance? In 40 kilometer per hour. So higher the velocity, higher air resistance will be. And soon what happens is weight becomes equal to air resistance. At that point, net force is 0, so acceleration is 0. This is why you can see in the graph that here the acceleration becomes 0. Now, so acceleration is decreasing because air resistance is increasing. Soon resisting force is equals to weight, then F net is equals to 0. So you can mention object will start traveling at a constant speed, so acceleration is 0. Alright, now part second, by drawing a tangent on figure 1.2, determine a value for the acceleration at t is equals to 0.01. So they are specifically asking you what is the acceleration at t is equals to 0.01, and 0.01 should be this point on the graph, right? So what you need to do here is you just need to draw a proper tangent. I'll give you a rough idea. So let's say something like this. No, this is a bit off. Let's try again. So something like this, and then you just complete your triangle and find out y2 minus y1 upon x2 minus x1. You know that gradient is change in y over change in x. So that is what you need to figure out. Some students are always doubtful that, sir, I understand that we have to draw a tangent and make a triangle, but how large triangle should we draw? It should be considerable in size. Do not make a very small triangle so that you can't even measure it properly. Make a decent sized triangle, and it doesn't matter actually. The length of the tangent will not affect the deceleration because the slope is constant, right, of the tangent. Alright, and the answer will come out to be in the range of 1.2 to 1.8. So a margin of error is always given. Alright, now question number 2. Figure 2.1 shows two identical pulleys P and Q held at rest on a frictionless horizontal surface. A load is fixed to a pulley P, trolley P, sorry, I mentioned pulley, these are trolleys. There is a compressed spring. Now, if it is compressed, it should have elastic potential energy, right? The trolleys are released. Now, just think about it. When you release the trolleys, this one will go towards the left, this one will go towards the right. So, they're mentioning that as the spring expands, it pushes the trolley apart. Trolley Q moves to the right at a constant speed of 0.36 meter per second. So, the mass is 1.2 and it is moving 0.36 meters per second. The mass of each trolley is 1.2. The mass of the load on the trolley P is 1.5. So, the mass of this trolley is 1.2, but the mass of the load is 1.5. So, the combined mass is 2.7. Alright, now calculate the speed at which trolley P moves to the left. Now, this is a question of momentum conservation. Initial momentum will be equals to final momentum, right? And initial momentum we will take when spring did not start to expand. So then initial momentum, everyone was at rest, so initial momentum it was 0. Now in final momentum, one of the trolley is going towards the right, the other trolley is going towards the left. Now we know that in maths, if one is going towards the right, we can take it as positive. If it is going towards the left, it is negative. Alright, totally your choice. If you want to take right hand side as negative and left hand side as positive, that is also fine. But we will use right hand side positive, left hand side negative. Alright, now which one is going towards the right? The trolley Q is going. What is its momentum? 1.2 times 0.36. Right? Plus the combined mass of trolley P with the load is 2.7, but now its velocity will be in the opposite direction. So we can mention negative velocity of P. Alright, and now when you solve this, your answer will come out to be nearly, let me put it in the calculator, 0.16 meters per second. Alright, you just transpose this thing to the other side, negative will cancel out negative, then 2.7 will be divide this, Vp you will get. Kinetic energy of the trolley Q when it moves at speed of this much, so half into mass of Q into 0.36 square. Mass of Q we know is 1.2, so half into 1.2 into 0.36 whole square. Your answer will come out to be 0.078 joules. State the energy transfer that takes place as a spring expands. So it is converting elastic potential energy to kinetic energy of the trolleys. So elastic potential energy to kinetic energy in trolleys. Alright, now we are done with this question. Let's start with the next question. Figure 3.1 shows a small block of ice floating in a beaker of warm water. State one way in which the motion of the particles in ice, see ice is a solid, differs from the motion of particles in water. Water is a liquid. So we can simply say that particles in ice vibrate about a fixed position and particles in water move throughout, or randomly you can mention your choice. Energy is transferred from water to the block of ice. State the name of thermal process that transfer energy from water to ice. Now they are directly in contact, so this should be conduction. Initially, there is this much mass of water in the beaker. Specific heat capacity of water is 4200. Calculate the energy transferred. We know that Q is equals to mc delta T and the change of temperature is 18 here. And mass is how much? 0.34. Specific heat capacity is 4200. And what is the change of temperature? It is 18. When you solve all of this, your answer will come out to be 2.6 into 10 to the power 4 joules. Now, the temperature of the water near the ice decreases first, which is very obvious, Explain how convection causes the temperature of all the water in the beaker to decrease. Now, convection is when particles heat up, they go upwards. Let's say this is your container and you have a heater here. So, and this is completely covered by liquid. Now, the particles with higher energy start moving upwards. You must have seen this when you are boiling water on a stove, gas stove, that particles start moving upwards, and the colder particles which have less energy, they start going down. So it's just a play of density difference. The particles with energy energy high energy start going upwards. This is the point. Now, so what I've written here is warm water rises up, cold water, the particles which have less energy, those I'm referring to as cold water. Cold water sinks. Now, density of the water next to the ice increases. Alright? So your ice is here, density of water next to the ice increases. I think this should be clear to all of you. Now, let's move on. State what happens to the internal energy of the water as the temperature of water decreases. See, if the temperature is decreasing, internal energy will decrease, as well as kinetic energy directly depends upon temperature. So the kinetic energy, average kinetic energy of the particles will decrease as well. Now, question number 4, this is a waves question. Lenses, the lens in a magnifying glass. So from this word only, it should be clear in our mind that this is that case where virtual and erect images are obtained. When you draw dotted rays like this to get the virtual image like this, right? So figure 4.1 shows the lens of the magnifying glass, its two focal points, all right? State what is meant by the focal point term. See, focal point, we know that when a light ray goes parallel to the principal axis like this straight, and when it touches the lens, reaches the center of lens, then it converges through the principal focus, the focal point or the principal focus, right? So what I've written here is that it is a point on principal axis where light rays parallel to the principal axis, just like we did here. If this is your focal point, so light rays parallel to the principal axis, this is your principal axis. Light rays parallel to principal axis converge through it then, right? Converge after passing through the lens. Alright, now a student using the magnifying glass sees a magnified image of an object. On 4.1, mark a point X of the object. Now, this is the last case of lenses, and just a minute here. This is the last case of lenses, and we know that the object will be placed between center of lens and the principal focus. So X I have marked here. Alright, let me draw the proper image for you as well. Let's say this is your object. So one light ray will go like this, and one light ray passes through the center of lens, and this will pass here like this. Then you extend them backwards. Somewhere here your image will form. And in order to see this, you can place your eye here or you can place your eye here. Totally your choice. Alright. So a point E, you can mark any of those points. Underline two words in the first list that describes the image produced. It is a upright and virtual image. It is also magnified, but that is not given here. So you will pick upright and virtual. The refractive index of glass used to make the lens is 1.5. The speed of light in air is this much. Calculate the speed of light in glass. So see, here we are going from air to glass. So I will use the simple relation here that N1 over N2 is equals to V2 over V1. Now you can also use the formula which is given in the syllabus guide, N equals to C over V. But I do not recommend using this formula. A lot of children are confused in this. Sometimes when they give us two refractive index, then children end up getting confused. How to use this? So instead of that, you can use this formula. N1 will be your medium 1, which is air, which is air, air's refractive index is 1. N2 is your medium 2, which is the glass, so 1.5. V2 is your velocity in glass, so let's call it velocity in glass. V1 is the speed of light in air, which is 3 into 10 to the power 8. Alright, now even if you use this formula, 1.5 is equals to 3 into 10 to the power 8 by V. It's ultimately the same thing, right? This and this is the same thing. So when you solve this, your answer will come out to be 2 into 10 to the power 8. If you solve this, it will be 2 into 10 to the power 8. If you solve this, it will also be 2 into 10 to the power 8. Alright? Now, state what happens to the wavelength of light as it passes into the lens. Now just think about it. You're going from air to lens. So you're going from rarer to denser medium. And we know that when light goes from rarer to denser, the speed decreases, right? And v equals to f lambda. If you're saying speed is decreasing, then the wavelength must decrease as well, because speed is always directly proportional to the wavelength. So the wavelength also decreases. Alright, you can mention that wavelength also decreases. I hope you're getting the point that when you're going from air to lens, you're going from rarer to denser medium, so the speed decreases. And if speed is decreasing, speed is directly proportional to wavelength. Wavelength must decrease as well. Alright, now converging lenses are used in spectacles to correct one problem with vision. State the name of the problem and explain how converging lens is used to correct it. For this, I have a photo for you. See. This is the problem and this is called as long-sightedness. In figure A, you can see that the light rays are forming behind retina. Let me see if I can edit this. You can see that the image is formed behind retina. It should form here. Retina is here, so it should form here. Now, when we use convex lens, then the bending happens more. So then they directly form at retina. This figure you can draw and then you can mention these points that the lens focuses the image on the retina. Without the lens, image forms behind the retina. And the other reasons are also given there. Just have a look. Make sure to take a screenshot of this. Alright, now let's move on. Now, describe how longitudinal wave differs from transverse wave. We simply know that in longitudinal, particles vibrate parallelly, and in transverse, particles vibrate perpendicular. So, I've written in longitudinal wave, particles vibrate parallel to the direction of energy transfer, and in transverse, they vibrate perpendicular to direction of energy transfer. Alright. Figure 5.1 represents a seismic wave produced by an earthquake. State whether this seismic wave is primary wave or secondary wave. See, primary wave is longitudinal, seismic P wave is longitudinal, you need to remember this, and seismic S wave is transverse. Alright, now this section looks like a rarefaction, then compression, then rarefaction, then compression, then rarefaction, then compression. And we know that compression rarefaction happens in longitudinal waves. So this is a primary wave because it is longitudinal. How do I know it is longitudinal? Because compression rarefactions are there. Alright, now let me erase this wonderful masterpiece. The wave represented in figure 5.1 has a wavelength, alright. Calculate the actual distance between J and K. See, we know that one wavelength is the distance between compression to compression. So we can say this distance is one wavelength. But they are asking till here. What do you think it looks like? I think it looks like 1.5 times the wavelength. Right? It looks like 1.5 times the wavelength. So you simply need to do that your distance is 1.5 times 1.2 into 10 to the power 4. You can solve this and your answer will come out to be nearly 1.8 into 10 to the power 4 meters. which is the correct answer. The wave in part 2 travels through a ground at a constant speed of this much. As the wave passes a certain point, the ground completes this many oscillations. Calculate the time that it takes for the wave to pass. Now, see, first of all, we know that V equals to F lambda and frequency can be written as V over lambda. Frequency can be written as 1 over time is equals to V over lambda, and time will be equals to lambda over V. What is lambda? 1.2 into 10 to the power 4 meters. What is V? 4600 meters per second. Solving this, you will get the answer for time to be nearly 2.3 something. Right? Now, this is the time taken for one oscillations. How many oscillations do we have? 5 oscillations. So you do 2.3 times 5. Your answer will come out to be nearly 13 seconds. One minute. There is some mathematical error here. Just a minute. So when you divide 1.2 divided by 4600, so it is coming out to be times 10,000. Oh, wait, my bad, beta. This is coming out to be 2.6. So you multiply 2.6 times 5, 13 seconds. Then 13 seconds will be the answer. Alright. Now, question number 6. Figure 6.1 shows an isolated metal sphere surrounded by insulating thread. The sphere is negatively charged. The charge on the sphere produces an electric field. You have to define electric field. See, electric field is the area where if a charge is present, it will experience a force. So, space or region in which electric charge experiences a force. It can be attractive or repulsive. Alright. Now, draw on figure 6.1 to show the pattern and direction of the electric field produced by the charge on sphere. We know that when it is negative charge, the electric field is inwards like this. And when it is positive charge, electric field is radially outwards. Now this is negatively charged. So you can draw 4 lines. Just try to make sure if they are equidistant, that will be better. Try to make sure they're equidistant. So something like this. Alright, you should draw at least 4 and try to make them equidistant from each other. Now, an earth metal wire is touched against the surface of the sphere. See, now the sphere is negative charge. The sphere is negative charge. Now they are just connecting it to the earth. This is what the earth metal wire means. Now we know that negative charge is here. So the electrons will start flowing through the wire and down to the ground. This is what earthing is for. If excess charge is there, then the electrons flow down the ground through the wire. So state what happens. Electrons start to move in the wire and move towards the earth. Alright. It takes a time of 0.514 nanoseconds. This is n, which will be 10 to the power minus 9. So it takes a time of this much. So we can say I equals to Q over T. Alright. Q will be how much? It should be mentioned here, which is 3.5 into 10 to the power negative 10. And then it is 0.14 into 10 to the power minus 9 seconds. When you solve this, your answer will come out to be 2.5 ampere. This is small n, which is nano, small m is milli, which is 10 to the power minus 3, capital M is mega, 10 to the power 6. Make sure to remember these. Now, define the term electromotive force. We know that electromotive force is the work done by the battery in moving a charge across the circuit. Potential differences across a component. There might be a lot of components in a circuit. Potential difference is different for all of them in series. But electromotive force is the total work done by the battery in moving a unit charge around a circuit. Alright. Now, the battery is connected in series with a variable resistor and 30 ohm resistor. The battery is made using 1.5 volt cells. Draw a circuit diagram that shows all the 1.5 cells connected to produce EMF of 7.5. So 7.5 divided by 1.5 will be how much? 6. 6 cells we need to draw. So we need to draw 6 cells. So what we can do here is, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and one more, 6. You can draw it like this, just make sure they are uniform. Then you need to make a variable resistor. Now, what is the symbol for variable resistor? Is it a box with an arrow? Yes. So you can draw a variable resistor like this. Then the normal fixed resistor is only a box, mention 30 ohms here. Then just connect the circuit. Label this as positive side, negative side, you will get the marks. Now, the resistance of the variable resistor can be varied from 0 to maximum resistance of 150. Alright. Using the axis, draw a graph to show how the current varies. So it is just asking you that already a resistor is there. Now we will also start operating the variable resistor, and we will start it from 0 and we will take it till 150 ohms. Right? So how will the current vary in this? This is what we need to answer. Alright. Now what we need to do is, first of all, find out when variable resistor is 0 ohms, then only your fixed resistor is working, 30 ohms, right? Then let's first of all find out current flowing. V is how much? 7.5. I we are figuring out, R is 30. So I will be 7.5 over 30, which is equals to 0.25. So this is the maximum current you have when the variable resistance is 0 ohms. When only the fixed resistor is working, so we can mention 0.25 ampere is the maximum current here. Alright, I think you understood this properly. Now, here the resistance of the variable resistor is 75. So now let's try to figure out the current when the variable resistance resistor is 75. See, now the total resistance will be from the fixed resistor 30 plus the variable resistor 75. So this is 105 ohms. Now apply V is equals to IR. Voltage is the same, 7.5. I you're trying to figure out, R will be 105. When you solve this, your answer will come out to be 0.07 amperes. So you need to mark a point here where the current will be 0.07. Let's say we are taking it as 0.07. Alright. Then let me mark this here as well. Then you can draw your curve like this. This represents that when the resistance in the variable resistor is 75, the current is 0.07, which is what we got here. Now let's also try for 150. When the R total is 30 plus 150 in the variable resistor, so current will be equals to V is equals to I into R. I will be 180 here. So I is equals to 7.5 over 180, which is 0.042 amperes. So now what you can do is mark a point here, 0.042, and make sure to match it here. Then you can connect this. Okay, I think you understood this properly. Now, the isotope thallium is radioactive. It decays by beta decay. All right. We know that in a beta decay, a neutron changes to a proton. A neutron changes to a proton, releasing a high-speed electron, which is a beta particle. All right. Now, when a neutron is changing to a proton, first of all, beta particle is released. Beta particle has a mass of 0, charge is negative. And now one neutron is changing to a proton. Do you really think that the mass number is changing? No, the mass number does not change in beta decay, but the proton number changes. See, neutron is converting to proton, right? So 81 will convert to 82. But the mass number is not changing because it is the sum of neutron and proton. Alright? Explain why this gamma emission does not affect the numbers in the equation. See, gamma emission is not affecting. The beta emission of thallium is accompanied by gamma emission from the nucleus. This is what they are asking you. Now, how should we answer this? Explain why this gamma emission does not affect the numbers in the equation A.1. Gamma emission does not have any mass or charge. This is what you can mention. So gamma emission does not have mass slash charge, so it will not affect beta decay or alpha decay. All right. Suggest one reason why nucleus is unstable. Nucleus is unstable because too many neutrons are there. So you can mention excess neutrons. Alright. Now, a sample of thallium is placed in a thick lead container. Figure 8.1 shows a narrow beam of beta particles and alpha radiation. Alright. Gamma radiation, sorry, not alpha. The narrow beam enters a region where there is a magnetic field. Now, magnetic field cross is represented by into the page. So, cross tells you that the field is into the page. You will have to use the Fleming's left hand rule here. Draw a line labeled beta to indicate path of the beta particle. You have to label the path of the beta particle in the magnetic field. Now, you have to apply the Fleming's left hand law rule, and the thumb tells you the force. The thumb tells you the direction of force. The index finger tells you the direction of magnetic field, and the middle finger tells you the direction of current. You can also remember it by FMC, force, magnetic field, current. Or you can remember father, mother, child, force, magnetic field, current. Alright. Now, if you point your middle finger towards the right, why towards the right? Because currently beta particle is going towards the right. Sorry, my bad. Beta particle is going towards the right, which means beta particle is electron. So if electron is going towards the right, current should be towards the left, because we know that the direction of conventional current is opposite to electron's flow. So if electron is towards the right, the direction of current should be left. So your middle finger should point towards the left. And your index finger, which is magnetic field, it should point into the plane. What do I mean by into the plane? The paper you are solving currently, your index finger should be perpendicularly pointed towards it. And when you align this, then your thumb will become downwards. It will show a downward direction. So the path will be like this. Alright, this will be the path. Now, draw a line labeled gamma to indicate the path of gamma radiation in the magnetic field. What do you think? Will gamma get deflected, or it will pass straight through? I'm repeating. Will gamma get deflected, or it will pass straight through? It will pass straight through because it does not have any charge. So it will go straight. This is for gamma, this is for beta. I'm repeating again, for beta particle, you need to use the Fleming's left hand rule, and your middle finger should be towards the left because beta particles are towards the right. So current should be towards the left. Alright, now let's start with question number 9. The sun is one of many billions of stars in the Milky Way galaxy. State the three regions of EM spectrum in which the sun emits the most energy. We know that ultraviolet, visible, and infrared is the answer. You need to remember this. Make sure to mention. Electromagnetic radiation from the sun travels at a speed of 3 into 10 to the power 8 meters per second. Alright. The radiation takes 500 seconds. So we can do this simply using speed is equals to distance over time. And we have to find out the distance. So distance is equals to speed into time. Speed is 3 into 10 to the power 8. Time is 500. Now, when you solve this, your answer will come out to be 1.5 into 10 to the power 11 meters. Alright. Now, let's move on to the next question. Approximately 4.6 billion years ago, the sun formed from an interstellar cloud of dust and gas. Alright. Describe and explain what happens as an interstellar cloud of dust and gas forms a protostar. Now, we know that due to the attraction from the core, due to gravitational attraction from the center, the nebula starts to collapse. So what I've written here is the nebula starts to collapse due to internal gravitational attraction from the core, Now, see, when the particles are coming closer, the collision will increase. So, the internal temperature increases as particles are closer. After this, what happens is soon we achieve the temperature for nuclear fusion. So, it's a cycle. But for this answer, you just need to mention gravity attracts the particles together. As a result, the nebula collapses and the internal temperature increases. Alright. Now, describe and explain what happens as a protostar becomes a stable star. See, in physics, you know that stability is obtained by when net force is zero. When the force towards the left is equals to force towards the right, and the force upward is equals to force downward. So, similarly, in this case, you need to mention it becomes a stable star when outward forces due to nuclear fusion. Just think about it, this is the core, fusion reactions are going on. So, outward pressure and forces are there. So, these outward forces and pressure are balanced by gravitational attraction from the core. Gravitation is always towards the center inwards. So when these two forces are balanced, then it becomes a stable star. So what I have written here is outward forces due to nuclear fusion reaction are balanced by gravitational force inwards. This is it. Alright. So we're done with the paper, guys. This was a good paper, one on the lengthier side. So in case you have any doubts, make sure to let me know.